In this video, we're going to take a little bit of a closer look at Ohm's law, which is the principle for all of the relationship between resistance, amperage, and voltage. And then we're also going to take a look at Watt's law, which has to do with power and the work that's being performed. So just some real basic background. A German scientist named George Simon Ohm invented Ohm's law by experimenting with electrical circuits, particularly with resistance in these circuits. This relationship is called Ohm's law. So the abbreviations used to represent the different electrical factors. E is voltage, stands for electromotive force. I is amperage, which is current. R is resistance, the electrical load where the power is consumed. Okay, and Ohm's law is best remembered by just creating this little pie chart, E, I, R. In calculating for E, cover the E and use the formula I times R. If calculating for I, cover the I and use E over R, which is E divided by R. If calculating for R, cover the R and use the formula E over I. So if you remember this little pie chart, you'll never go wrong. Okay, you just have to know if the number's one over the other, it's division. If it's next to each other, it's multiplication. Electrical circuits are sometimes compared with water circuits. In a water circuit, pressure pushes the water through the circuit. The water flows at a gallon per minute or GPM rate. It flows against the resistance of the friction loss in the pipe and the components in the circuit. In electrical circuits, the water pressure is compared to voltage. The water volume in gallons per minute is compared to the amperage, and the friction loss in the pipe and components is compared to the resistance to electrical flow in the wire or electrical load. Ohm's law has determined that the voltage equals the amperage times the resistance. So we start with the basics. E, which is the voltage, I times R. Now, if you start messing around with the formula and use algebra, I know, tough thing to deal with, but I is E over R. Okay, so amperage equals the voltage divided by resistance. Then we can take it a step further and say the resistance equals the voltage divided by the amperage. These three formulas can be used to calculate a circuit's performance. As long as you know any of the two values, you can find the third. So suppose that you measured resistance of 60 ohms and the current flow of 2 amps of a heating coil in a circuit, but you want to know what the supply voltage should be. If you really want to, you can use the formula E equals I times R. Now, if I measured the current flow, wouldn't you also just use your meter to take in the supply voltage reading? Yeah, I would. But it's important to know how this all comes together. And the important part here is the resistance heat. Okay, so again, if this is a motor, it may not actually work out. But in this case, it's resistive heating. That's why it's a heating coil. Okay, and Ohm's law will work out. Okay, suppose the voltage to a heater is 220 volts and the resistance of the heater is 10 ohms. What should the amperage be when the voltage is applied to the unit? You're going to use the formula I equals E over R to find out. So 220 divided by 10 is 22 amps. Now this is more important because if you're installing an electric heat strip or a heat coil someplace, like in an apartment or a condo or someplace like that, you have to make sure that the wiring and the circuit breaker can handle the load. So this is an example that you're going to use more frequently. So to measure these readings with a volt-ohm meter, okay, the ohm portion of the meter is used to measure the resistance of a component. To get the correct ohm reading, it has to be isolated from the circuit with no power on it. Okay, now, electrical power is measured in watts. P stands for power. A watt is the power used when 1 amp flows with a potential difference of 1 volt. So power can be determined by multiplying the voltage times the amps flowing in a circuit. Watts, volts times amps, or P equals E times I. Power equals voltage times amps. Okay, you can also on this one do another if you wanted to. Okay, let's throw this up here. okay, you can do your P E I. Okay, so if you wanted to, you can do another pie chart. Okay, and drawing with a mouse sometimes doesn't work too well. Okay, you can do another pie chart, and again, just as with the Ohm's law, Watt's law will work out the same way. Okay, a consumer of electrical power pays the electric company according to the kilowatts used in a certain time span. It's usually billed in kilowatt hours, or kWh. A kilowatt is equal to 1,000 watts. Okay, so it's basically saying how many, your meter outside is reading how many watts is used in an hour. Kilowatt hours. To determine the power being used, divide the number of watts by 1,000. So P equals E times I divided by 1,000. That's how many kilowatt hours, that's how many kilowatts are being used. Magnets are classified as either permanent or temporary. Permanent magnets are used in only a few applications that air conditioning and refrigeration techs work with. Okay, electromagnets is the type of temporary magnet that's used in many electrical components in the HVAC field. A magnetic field exists around a wire carrying an electrical current. If you loop the wire several times, like into a coil, that magnetic field increases. If the wire is wound into a coil, a stronger magnetic field is increased. The coil of wire carrying an electrical current is called a solenoid. This magnetic field can be used to generate electricity and to cause motors to operate. Now, let's talk a little bit about how Ohm's law works in series circuit. Remember, series circuit is a circuit where there's one path for electricity to flow. So voltage, which is E, voltage drops across each load are added together to equal the total voltage applied. So your formula for voltage in a series circuit, the total voltage, ET, equals the voltage drop across each load. Okay, so every load adds up together to get the total voltage. Current, which is also known as amperage, is constant throughout a series circuit. Current stays the same. No matter where you measure it in a series circuit, current will be the same. Resistance, okay, the total resistance is equal to all the individual resistances in that circuit. So to get your total resistance of the circuit, you add the resistance of each load in the circuit. So RT equals R1 plus R2 plus R3, and so on. Power, which is measured in watts, is equal to all the individual powers added together. So each load is using power, okay? So you add it up just like you would do with voltage and resistance. So we have a theoretical circuit here. We have two loads, okay? Load 1 and load 2. Someone has measured the amperage, okay, across load 1, or the total amperage of the circuit. It's 2 amps. Okay, we know that we can fill in the rest of this circuit. Okay. Okay, I mean, I know I could put a 2 there, I could put a 2 there. Okay, power adds. So I can come over here and I could say my total power is 288 because it adds up. Okay? Now, if I know my amperage and I know my power, how can I come up with my voltage? Okay? I can come up with my voltage drop across this load because P equals E times I. Okay? Remember our little P, E, I. So if I know my voltage, I can divide the power by the amperage. Okay, so 2 by 50, okay, we would put 50 here. 2 into 188, okay, is 94. Okay, we add that up, okay, and let's just use my handy dandy calculator here since I'm just want to make sure we give the right one. So we have 144. Okay, now E equals I times R, or R equals E divided by I, right? Okay, we think about our Ohm's law. E I R. Okay, so if I take that 144 divided by 2, we come up with 72. If I take 94 divided by 2, I come up with 47. If I take 50 divided by 2, I have 25. Now, because resistance adds, I can do a quick check to make sure this number's correct by adding my 25 and 47. And I come up with 72. That is correct. This all adds, okay? So that's how you solve this. Okay? There's solutions there. Okay, another one here. Okay? Again, same type of idea. We have some numbers, but not the rest, okay? So, I can come down here, okay? We know my amperage is constant, right? Okay, so we know that that's going to be constant. Okay, E divided by I is RT. So I could take my 120 divided by 2.4, I get 50. Actually, let me do that again. We have 120 divided by 2.4, it's 50. Okay. Now, here, 20 times 2.4, because again, we're going to use Ohm's law, okay, is 48. Now, if you remember, in a series circuit, voltage adds. So I could take my 120, minus out the 48, and I could find my 72. Once I have my 72, I could divide that by my 2.4 amps, and I'll come up with 30. Okay, and again, I can double check those numbers by adding those together. Now, all we need is our power, okay? Power is E times I. This becomes very easy. 48 times 2.4, 115.2. Okay, 72 times 2.4, 172.8. Okay, 120 times 2.4, 288. Now, if I add these two together, I come up with 288. And again, pens with mice are tough to write with. So we'll go to the next screen. That gives the answers. Okay, so again, this all does add together. And this is how you solve a circuit, a series circuit problem. Now, we also have parallel circuits we have to deal with because everything is, most loads in HVAC are not in series. So we got to deal with parallel circuits. Okay, changes up the Ohm's law a little bit. So let's talk about parallel circuit rules. Voltage in a parallel circuit is equal to all branches of the circuit. Okay, voltage to every branch of the circuit is the same. Easier way to put it, every branch of a parallel circuit gets supply voltage. total amperage is equal to all the branches added together. So your total circuit amperage is you add it all together, every branch added together. Resistance is the one that's a little bit strange in parallel circuits. We got to do a little bit of math on that one. Total circuit resistance is always less than the smallest branch resistance, and that's one of the most important things you can remember. Total circuit resistance in a parallel circuit is less than the smallest branch resistance. There are few ways to calculate resistance in a parallel circuit. Okay? Remember, Ohm's law says R equals E over I. Okay, there you can use total circuit resistance. Okay? By that, if you know your total voltage and if you know your total amperage, you can find your total resistance. But that doesn't break it down on a component or by a branch level. Okay, the other way is if you have two resistances, you can use the formula R1 times R2 over R1 plus R2. Okay, so if I know my resistance of my first load, okay, and the resistance of my second load, okay, I can find my total. You can also use, if they're all the same, okay, if every resistance in the circuit is identical, you can divide it by the number of components in the system. So R1, R2, R3 are all the same. RT equals 30 divided by 3, so total is 10 ohms. Again, the total resistance is less than the lowest resistance in the circuit. Then we can use the reciprocal method. This always works. RT equals 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3. It's called the reciprocal method. Anytime you divide a number by 1, or 1 into a number is what I'm actually looking for, it's called the reciprocal. Okay? This you only want to do with a calculator. So, if we have these, again, we have two loads in parallel, okay? We know that the voltage, okay, and I'm going to do part of this here and then we'll look at the answer, but I'll get you, let me just, okay. We know voltage is the same. Okay, so if one branch is getting 120 volts, we know that every branch is getting 120 volts. Okay, so now here I have two like resistances. Okay, so I can use my my total resistance. Okay, we can divide this by 2. Okay, if I go back a couple slides, okay, actually, okay, we know that I can say these are identical. So I could take my 2,000 and divide it by 2. So my total resistance will be 1,000, less than the lowest resistance. That's correct. Okay, now, once I have my voltages, okay, and I have my resistance, can I find my amperage? Yeah, because I can go back to using Ohm's law. So we can take our E over R. So I take my voltage, which is 120, okay, and I can divide it by 2,000, and I have it's going to be a 0.06. It's a very small number. Okay, and it's going to be the same on both of these, right? Now, what did we say about amperage in a parallel circuit? It adds. So 0.06 and 0.06 is 0.12. So we're talking very small amperage. Now, I could take, okay, my power is E times I. So I could take my 120 times 0.12, and I'm going to have 14.4. And that's a 14. Again, sorry about the writing with the mouse. I could take 120 times 0.06, okay, 7.2, and I can take 120 times 0.06, okay, and I'm going to come up with the same thing. The numbers are the same for both loads. Now, what does this tell me, okay? So if a customer's telling me that their power bill is way too high because this electric heating system or whatever it is, I can look at this, the total power. Okay, this is in watts, okay? So the customer's being billed on kilowatts per hour, okay? So I could say my 14.4 divided by 1,000. Okay, so if I want kilowatts per hour, okay, this customer's is only using 0.144 kilowatts per hour to run this appliance. Okay, that's not going to make a big difference on a power bill. Okay, and let me give you the actual fill in the numbers just so you can read it. Okay, so again, this is what we just went through. This is just the printed answers. Okay, give you a second here and let you see if you can do this one. Okay, again, we've given you the resistances. Okay, your total resistance will be less than the lowest resistance in the circuit. You'll probably have to use the reciprocal formula here. Okay, once you find your, you can also come straight across here and use your amperages. Okay, the way I would do this is we know, okay, once you have this here, okay, once you have this number here, the resistant total, you'll want to find your voltage. Okay, that's Ohm's law, E times I. Find your total voltage. It's going to be identical all the way here. Then you can find your amperage for each blank. Then you can come down and find your powers just by multiplication. The answer to this comes out, okay, it's 115 volts straight across the top. You divide your resistance by that, okay? Then you can come down and find your amperages and your powers. Okay, so Ohm's law works both in a series and parallel circuits. Ohm's law will not work properly with inductive loads, okay? Inductive loads like a motor winding. Okay, it works very well with anything that's resistive in nature, but induction, where there's a magnetic field actually that affects the resistance, that's where Ohm's law does not work 100% well. You do need to practice with Ohm's law. It does show up on every single certification and licensing exam I've ever taken.